So thanks very much for the introduction. I am very happy to be here. Thank you for the organizers to invite me here. It's my first time in the Freie Universität, a very nice place. So pleasure being here. And also first time at this conference. I've already had a lot of conversations, discussions. It's a super nice meeting, super nice being with all of you. I guess my presentation will be a bit different in the sense that I will not be talking as much about software architecture, but rather my angle is to talk a little bit more about kind of challenges we have in software which flies onboard spacecraft, and just to show you that that not everything possibly is to be solved by software architecture, but maybe there are some things that you can come to me later and say, look, but actually there are some architectural issues there, and maybe you can tackle the problem by changing your architecture or something like this. So I will be very happy to follow up, and maybe, I don't know, discuss this after my talk. So I can skip this one because this summarizes the work I've been doing. Basically, what I want to say is, or what I want to start with, doing spacecraft flight software is super cool. It's amazing work, and I guess the important thing about it is that you sort of stop thinking about software and you start thinking about the system, about this beast which is in the fairing there. Because basically there are two main things which happen with the flight software. One is that you write your software, you launch the spacecraft, and you never see the thing again. It's flying in space. There are exceptions to this. If you worked on ISS experiment or on space shuttle or Orion or something like this. But most of the times you don't see the software again. And then second thing is that the software is basically for the first time sort of testing the functionality because it has never been in space before. Everything you have tried, you tested, you designed, you use all kinds of simulators, but in reality, this is the first time the software flies. Of course, again, there are exceptions, like if you have constellations of several hundred satellites, then that's something different. But if you work on this kind of satellite, this is what it is. And yeah, so here I'm in the Mission Control Center, waiting for the signal from the satellite. Once again, exciting work. It's also teamwork. A lot of people working on the spacecraft. And it's not just software. You have to work with people doing propulsion, people doing optical instruments, people doing materials, people doing solar panels, batteries. Like if you just think about power distribution, you have experts who are chemistry experts doing batteries, people who are experts of solar panels, people who are experts with electronics and things like that. So it's amazing teamwork, and then it's a lot of responsibility. There is a picture of the cathedral in Antwerpen where we had a meeting with this team, and there was the moon there, and I was working. We spent basically the whole day there designing docking sequence of our spacecraft to the lunar station. So, and then we were looking at this and we thought like, okay, this is 400,000 kilometers away. The whole thing, the whole day we spent on some piece of software which will make the 4 astronauts which will be sitting inside that spacecraft to dock with the rest of the station. It has to work. There's no way it does not work. So it was amazing to see the moon like this and having this kind of feeling. So what I want to talk about is a little bit about ESA, a little bit about what actually is spacecraft flight software, and some challenges which we have. As I said, it's not always to do with software architecture, but all kind of challenges. And yeah, I thought it's almost mandatory to talk about how we use AI because there were so many AI talks that it seems like this is must. And about some failures we had and how software can help, something about software frameworks, lessons learned. Obviously, the bar was set with the keynote this morning super high, so I cannot be as good, but I will try my best. Okay, so a few slides about ESA. ESA implements the space program for Europe. It's 23 member states and 3 associated states, 1 cooperating state, which is Canada. So it's not exactly matching the European Union states. 6,500 people working for ESA. This year's budget is over 8 billion euro. We target all sort of, we address the whole space domain completely, all areas of space flight, starting from what we call science and exploration, which means that we have spacecraft which explore the planets of the solar system. Then we have some observatories looking into deep space at some stars and things like that. And then we do also, we send astronauts to space as well. Then applications, what I mean by applications is, we have navigation satellites, Galileo, which is actually the most precise navigation constellation today. We have Copernicus program, which is set of Earth observing satellites, which also not only monitor the Earth, but also they help like weather forecast and this kind of stuff. And then we have also telecom satellites. And we are building a constellation called IRIS², which will be sort of European capability to have, you know, something like Starlink is done by the United States. Safety and security is about satellites which are monitoring the Earth for the sake of like natural catastrophes and this kind of stuff, monitoring the Earth again, but also monitoring the space weather and also asteroids which are approaching the Earth and doing some sort of research how we can deflect the asteroids and this kind of stuff. And enabling and support, finally, we have a set of launchers, family of launchers called Ariane and Vega. We have Mission Control Center, and we have also a set of ground stations around the Earth. We have multiple offices around Europe, headquarters in Paris, and I'm specifically located here in Nordbike, which is along the coast, something like 40 kilometers from here. And that's called, it's on the next slide. I want to mention also that we are launching from French Guiana, so that's our launch site in Southern America. And now ESTEC, that's where I work. That's the European Space Technology Center. Basically, all the projects are defined and controlled from there. There's more than 3,500 people. And there is a lot of labs, a huge test center with vacuum chamber, shaking, you know, like shaker, big shakers, and a large space simulator and this kind of stuff. That's what we do here in the Netherlands. There is a lot of missions we have launched, for instance, this year, already more than 30 missions, including our involvement on Artemis mission, where we flew the 4 astronauts around the moon, and we provided for Orion spacecraft, basically the propulsion and power system. We flew multiple other missions, let's not spend too much time there. A lot of missions planned for the second half of the year, including, for instance, for our mission to Mercury, which has been going to Mercury for, I think, something like 6 years. It will arrive to Mercury in November, I believe. And then that's called Bepi Colombo. And then, for instance, the Hera mission will arrive to Didymos asteroid, also in autumn. So we will have quite a busy autumn with a lot of exciting missions. And that was the introduction. And now, what is actually spacecraft flight software? So, it's very easy. Spacecraft flight software is the software which flies on the spacecraft. So you can imagine that there is some software also on the ground station or let's say on the mission control system. But that's not the software I'm talking about. I'm talking about software which is there and communicates via ground antennas with the mission control center. Just to give very quickly overview what that kind of software can do, just that you have some imagination. So it's in charge of autonomy. So there the most important thing is controlling the attitude and orbit, but also thermal control, managing modes of the spacecraft, like for instance when it's just moving to the target orbit or something like that. Health monitoring, power generation monitoring and distribution of power, including deployment and rotation of the solar arrays. Then communication with ground. All the telecommands which are sent to the spacecraft are processed by software, and as well all the messages, what we call telemetry, are sent by software back to ground, so it's a super important feature. And then mission management. But what I mean by mission, you know, the only point why we fly spacecraft to space is to collect some data, right? Otherwise, there's no point. Unless we are talking about human exploration because we want to have people out there, because we want to push the limits. But otherwise, it's the data. We do some scientific measurements, observations, things like that. We needed to collect their data and get it back to Earth. So when it comes to this, again, a payload software is special kind of software which is actually doing all these measurements and the science operations. And then it's the data collection, data processing, compression, and distribution back to Earth, or maybe storing it on board and then sending it by antennas back to Earth. So overall, flight software is basically kind of a brain of spacecraft, right? It coordinates all the subsystems there. I see people are laughing because it's apparently AI-generated picture, but it's very well generated, I have to say. And now, what do you think is the most important feature of the software, of the spacecraft flight software? Any ideas? Like really the one which is super important. Sure, but in terms of function. A lot of good ideas. Sorry? As well, good idea. Yeah, all of these are very good things. Last one. Yeah, also very good, but yeah, I mean, it's a nasty question. No, in the sense that all of this is super important and all of these things which I named before, but the super important thing which is making software special is that you can make updates of software. You cannot update anything else, but you can update the software. So if there is any hardware failure, anything which is problematic with the spacecraft, the only thing you can do is update the software. There's basically nothing else you can do. You can change the way you are operating the spacecraft. You know, if there is a command which kills the software, for instance, then you say, don't use that command or something like this. But the fact that you can update the software is extremely valuable because very often some hardware does not work as it should. For instance, the thermal limits are a little bit off or something like that, but you can change the software to change this. So it's extremely important feature. Then another one which sounds a little bit silly, I would say, that it has no mass, you know, it does not weigh. You know, it's, you launch it and it does not add to the mass of the spacecraft. But it's not as silly because every kilogram of mass which you have to launch costs a lot of money. You need that launcher to bring the mass to space. And if you, for instance, upload new version of software which is doing some more stuff, it weighs the same. It's cool, right? It's not making any difference. Of course, if you need super, like, order of magnitude better software, you might need bigger hardware or something like this, but that's another matter. Software also, well, cannot fail because of the things I mentioned, and has to adapt to all sorts of unforeseen events. And that's where I bring this example. It's our JUICE mission, which is flying as we speak to Jupiter. It was launched already in April 2023, and actually it started to be designed in 2012, just to give you some sort of perspective how long it takes to develop such a mission. It will arrive to Jupiter in July 2031. So it's a really long time to get there. Jupiter is usually roughly 500 million kilometers from the Earth. Between 500 million, that's the best case, and billion is the worst case, just to imagine. It does not fly there directly. Instead, it sort of, by a lot of flybys, it sort of gets to an orbit of the Sun to reach the orbit of Jupiter. So, and that mission, another fact I should say is the approximated cost of the mission is 1.7 billion euro for a single spacecraft, including everything. So what happened there, shortly after launch, this big antenna, which you can see, which goes vertically, was supposed to be opened, and it got stuck. And suspected cause of this was that a pin was stuck, and then actions which were taken. Using software, it was possible to rotate the spacecraft, sort of to put sun on the pin, to make it hot, and then rotate again to make it cold. The difference between these two could be roughly 250 degrees, like plus 100 degrees, minus 150 degrees, something like this. And it was believed that if you do this, then the pin will get unstuck. And this did not work, so instead they started to prepare a sequence which was to do something with the thrusters, basically to shake the spacecraft or something like this. But in the end, they decided to do something different, because the sequence was to open the antenna, sort of first the most outer elements, and then the next one, and the next one. And then the outer one did not open, and they decided to try to open the next one, and the shock caused the pin to unstuck. Actually, it deployed. So I guess what I wanted to demonstrate is that for a lot of these things, this kind of flexibility is implemented by software. The fact that you have the diagnostics, for instance, the fact that the antenna did not deploy was seen by the control algorithm, which did not see the oscillations which were characteristic for the antenna being opened. So from there, they realized that the antenna cannot be opened. I don't think there was a camera pointing into that direction. I'm not 100% sure. Then this kind of flexibility that you can rotate the spacecraft and things like that, again, you have to have, of course, we have the experience to do this, so it's normal to have these kind of features on board, but you have to prepare to be able to do this kind of stuff. And yeah, the flexibility of the control algorithm, for instance, it needs to be designed with this kind of problems in mind. So I guess lessons learned, software can support contingency situations. And then another one, it was important to have the model of the spacecraft on ground so that they were able to test this thing with the different sequence of unfolding the antenna. Another example I want to show, and I have to speed up, I think, it was the Mars Express spacecraft, which was launched in December 2003, and it was planned for 2 years mission, and instead it kept operational. It's still operational right now, and around 2017 they realized that gyroscopes, so some units which are basically which are used to determine like the direction of the spacecraft, basically, were basically projected to fail in 2 years. So what happened was that 15 years old code had to be hacked to change it, to use star trackers for the navigation rather than the gyroscopes. These were used only occasionally. And that kind of code was uploaded 1 year later in April 2018. And thanks to that, the gyroscopes work even now, and they are projected to work until 2034. So again, this demonstrates the fact that updating the software is super important because you can extend, the lifetime of the mission. Interestingly enough, the way we do this, but that's another matter, is not that you upload some application or something like that, but you upload the whole image to update the software. But yeah, I think it has something to do with the fact how we do this. So this, I wanted to show that there is a lot of, this is called FlatSat, and it's basically a model of all the hardware of what we call avionics, which is on board a spacecraft. This one is a METOP second generation spacecraft made by Airbus. And we use it to test the software. It's one of the steps to test the software, because you cannot test everything on the spacecraft, because the spacecraft is used by other tests and other things. It's being integrated. It's not possible to do all the tests on the spacecraft. And there is software not only on the main onboard computer, but on the star trackers, on the GNSS receiver, on the payload computer. There are many computers with software on them. Now I got to some of the challenges, like characteristics of spacecraft flight software. So I guess the most important one is that it's embedded software, which is real-time software. Real-time meaning not real fast, but real-time meaning that the function, the fact that the software works is evaluated not only by the fact that it delivers the function, but also that it delivers it on time, right? Time is also important aspect. Typically how it works is that there are, I don't know, 30, 40 threads which constantly do something, some control algorithm with the frequency, I don't know, between 1 Hertz, 10 Hertz, 40 Hertz, and every slot, 20 milliseconds or so, there is like a deadline, and by that time, the function needs to finish and make the computation. That's what real-time software is. And then why this talk is called When Less is More. We work in a very harsh environment where there is strong radiation there, depending on which orbit the spacecraft flies. And that means we have radiation-hardened hardware, and which means that we have specialized hardware which is by far not as powerful as the hardware you are used to. So to give you an example, typical spacecraft which fly today is something like 100 megahertz processors. The future spacecraft which are in preparation, something like 250 megahertz. Quad-core is our typical processor developed by Geissler in Gothenburg. And we are working on 1 gigahertz processor, which would be octa-core. So just to give you the idea. And then how we do this is, the interesting thing is how we approach many of these challenges is not that we are super robust when it comes to architecture, keep the architecture and it will work. It's more about the process. We have very strict standards which mandate exactly which kind of documentation you have to deliver, how you should code, and this kind of stuff. I will get to that in more detail. Safety and reliability, obviously these things have to work reliably, so that's another challenge. And again, I'm mentioning there independent software verification and validation. So again, the focus is on the process. And independent verification and validation means that we, for critical software, not we, but in fact, we don't develop the spacecraft. We have suppliers who develop the spacecraft for us, and they have other suppliers who develop the software. And they also have to hire third party, which is checking the software independently. So it's additional cost, that you have someone else who is checking your software, verifying the requirements, verifying the design, verifying the code, and running independent tests as well. Another challenge we have is complexity. Although we are not talking about millions of lines of code, but more hundreds of thousands of lines of code, something like this. But it's also the complexity, given that it's real-time software and very tightly coupled and things like that. So we use software frameworks, we use advanced verification validation techniques, we use a little bit of model-based software engineering. System integration is another challenge. We use software which is provided by multiple parties. And again, because of this tight coupling and timing, the integration is quite tricky. Also, what is a little bit tricky, but I will get there, is when your software runs on hardware and the hardware is usually delivered late or is specified late. So that's another problem. And then configuration management and updates. Some of the software is used on multiple satellites. There are late changes, updates in flight, and we have to manage all that. And this becomes more complex for large spacecraft constellations. Basically, we try to move from like text-based specifications and some drawings, manual coding, testing, towards more executable specifications, automatic documentation, ultimately bug-free software, using model-based software engineering, state machines, model checking. But what I want to say is, this is more, that's where we are going, let's say. We are not always successful doing this. For some subsystems, we use this. For instance, for attitude and orbit control, we use MATLAB, and then from there we generate the code, and that's working. But there is one but, which is important. We don't trust the generated code, which means that this kind of mantra, what you do, why you are doing model-based software engineering, is to have correctness by design. And because we don't trust the code generator so much, we anyway test the generated code the same way we test handwritten code. There's no difference for us. There is a little bit of game change when it comes to large constellations, like probably Starlink, 6,000 satellites. Ourselves, I mentioned we work on IRIS² 290 satellites. There are some other constellations. We were used to one-off satellites, which were like the JUICE one I presented before, which is sort of one-off mission. There are some product lines and reused libraries and this and that, but it's one-off satellite. And we have more and more these kind of constellations where we need to have a little bit different mindset, which means it's a bit of serial production, even of the chips. It's not like that you have the target hardened, radiation hardened processor and several models which are not radiation hardened where you test the flight software, but instead you have a little bit different scale, because if you are launching 200 satellites, then you need production of 200 flight models and some number of the test models, etc. So there is definitely, there are challenges linked to that when it comes to autonomy, because again, we cannot operate the satellites the same way if there is 200 of them. So it cannot be that there is 200 people, talking the old style to the satellite. It's not working like this. So that's another challenge which is relatively recent. Obviously, a challenge to do with configuration management with all those satellites, and how we do operations, how we do maintenance. Very often, software ends up being on critical path because it relies on the design of the hardware. And very often that comes late, or there are changes, or we get simulator which is not really accurate, and therefore we need to change the software. So what happens is that software is often blamed to be late and delaying the mission, but in reality it's more complicated. Software is the last thing which you can change to make everything work. So it's sometimes blamed for no good reason, but says flight software engineer. But overall, it's believed that the complexity, size, and verification of flight software are underestimated and causing troubles. And then also worldwide, there are some examples of big failures which are caused by software. Some of them I mentioned there, be it NASA or Japanese Space Agency or ESA. And I'm going to talk about one of them, which is relatively famous in my domain. I'm not sure all of you know this one. And it's the Ariane 5 maiden flight on 4th June 1996. And what happened there was that Ariane 5 reused part of the software from Ariane 4. And then the behavior of Ariane 4 is slightly different. And then there was a variable called horizontal bias, was basically overflow. It was converted from 64-bit floating point number to 16-bit signed integer, and there was an overflow. There are several other facts related to this. One, why was it not checked? Back then, and that's not completely software issue. It was believed, let's use this processor for this, but the requirement was to use only 80% of that of the CPU on that processor, and it was not possible in the Ada language, which was used back then, to have the overflow checked on all the variables which were in the system, because that basically increases the CPU load. So 4 of the variables were checked, 3 of them were analyzed to be okay, and this one was analyzed, but on Ariane 4, not on Ariane 5. The other thing is that the software which failed was actually not used. It was only supposed to operate until the launch minus 9 seconds. So the software did not need to operate. But anyway, 37 seconds after launch, the trajectory was off, and then the self-destruction system destroyed the launcher. The cost in dollars, because we did not have euro back then, is 370 million estimated, $50 million for the launcher itself. And because there was scientific payload for cluster satellites, it was 320 million more lost. I guess lessons learned from this, the most important part is the reuse. And you can imagine that, reuse has to come with some sort of contract, how you should reuse that kind of software. Like with some sort of set of preconditions, post-conditions, some way of formalizing, the constraints, how you can use that software. And this was not done. The failure would not have happened if the building block design contract was documented and checked. And the other way around, of course, it's important to validate the envelope in which some software is running, to see what are the conditions, what is the execution environment. So this did not happen. And then there are some other lessons learned from this. To test all realistic scenarios, use end-to-end simulation, do fault injection, robustness and stress testing, this kind of stuff. But also when it comes to software architecture, things like if the system design was in such a way, is done in such a way that one process does not kill the whole software on the spacecraft, on that processor, but because it was single space or single address space operating system, it basically killed the whole processing on that computer. Another one is to have different kind of redundancy concept, because in fact there was a redundant computer there, but it was running exactly the same software. So that software failed as well, like 1 second later or something like this. But you can have concept which we call dissimilar software. So basically to have another supplier develop the same software again, but differently. But obviously that's not for free, So, but it's an option. And then I guess, if there was some sort of intelligent exception handling, this would help as well. And then one of the lessons learned led also to creating this independent verification and validation process, which is at ESA. So now I have some sort of set of best practices, what we do, how we work with flight software. I will try to go through it quite quickly because I can see that time is flying and the next session is right after. So basically, really, the most important thing how we tackle this kind of critical software is to follow very strict engineering process. That's how we approach it. And we tailor it based on software criticality, and I will talk a little bit about the software criticality later. We are strictly driven by requirements, and we have traces from requirements through design to code and tests, which are testing each of the line of the code and requirements. We have full traceability between all of these things. We have many types of tests, starting with tests at software level only, which is maybe in some simulated environment. That's okay. But then we validate every requirement on realistic hardware. And then we have some other, what we call system level tests, where we integrate with the rest of the spacecraft. We have functional tests. We have what we call operations tests. Like if you imagine that Earth orbiter flies once per 100 minutes around the Earth and twice per the orbit is dumping the data to ground station, and it's scanning on the sunny side for 40 minutes. So there is a test which is mimicking exactly this kind of stuff, which is happening every 100 minutes, is always the same, just to see that the software can cope with it. There are no buffer overruns or something like this. It's important to have realistic data to test the software. And then we do something called schedulability analysis, so some mathematical analysis to show that the real-time properties of the software are met. Our mantra is to keep the software simple. That's, again, back to when the title of the presentation, which is when less is more. You know, we really implement only the essential capability. To give you an example, with fault management, you know, often it's not a good idea that the software would try to analyze what precisely happened and having some complicated logic to nail it down to, actually this variable is wrong, so, you know, I go to this execution path and that, yada. It's easier to say, oh, it failed. Okay, let's just reboot and that's it, you know, and you save many, many lines of code. If you can afford it to handle the failure this way, then it's better than to be too smart and add many, many lines of code to implement this. We ban having any unused code or deactivated code. And another mantra is test as you fly, fly as you test. I guess it's self-descripting. And then other good practices we have coding standards, defensive programming, we gather code quality metrics of all sorts. We have design margins. For instance, at preliminary design review, we need to have 50% of memory free, 50% of CPU not used. At launch, it's 25% of memory not used and 25% of CPU not used, just in case of having to update the software later. We do all sort of analysis, code inspections, all sorts of things. Also, I mentioned that we define criticality of software, and that's defined, it's not just some guesswork, it's defined based on the consequence. You know, what is the severity of the failure? So category A software is like for human spacecraft, or in case there is the failure would cause some big catastrophe, you know, like having some damage on the ground or something like that. That's the one end, which is criticality A. And on the other hand, criticality D is basically ground software. And then B and C is somewhere in between. And related to it is cost, because you know, we have strict requirements when it comes to code coverage by tests, which is 100% decision coverage and statement coverage for class criticality A and B, and MCDC coverage, which is basically checking every condition, every Boolean variable which is impacting decision needs to be verified. So that's additional test cases, and that's for class A. And on top of it, also coverage of object code by tests, in case there is no clear traceability between source code and object code. When it comes to AI, and I got to that point, so there are two ways how we use AI. One is for the production of software. We don't do any vibe coding or anything like this. Basically because we have all of these super strict procedures, standards, we anyway need to have full traceability with the design and with the tests and having full trace how it is all working and tested and verified. We just don't see that it would help us that we generate some code. But obviously, I can see long term that it is possible that you take the standard and you ask the LLM, like, okay, you have to do it this way. You need to generate the documentation for me, for the humans to verify it. But right now, we don't do it because it looks like too complicated and we don't trust it, basically. I mean, this business is quite conservative, so we have to be careful there. Otherwise, yeah, we use AI for all sorts of verifications to verify consistency of requirements, all this traceability, finding code defects, and defining even test suites and things like that. And for that, it has been used, and it's quite successful, I have to say. When it comes to flying AI on board, we are limited, once again, by the environment in which we are flying in two ways. One, that the GPUs which you use in computers for AI are not radiation hardened, but we are experimenting with some software which is actually more powerful and radiation hardened. But another one is that these processors need significant amount of power. And that's another constraint. You know, we cannot afford flying. Typically, we generate power by solar arrays. We cannot afford to have 100 square meters of solar arrays just because we fly AI. But we are getting there. Example applications where we can use AI on board is like image processing, you know, basically to drop some images which are detected to be bad, unusable, which can help saving the bandwidth because the bandwidth to communicate the data back to Earth is limited, obviously. Then things like AI-based mission planning, you know, this would be a nice feature. Today, it's always done by humans. Some of the control algorithms could be assisted by AI, like proximity operations and things like that, you know, like docking operations. I can imagine that we can use AI. We don't do it, but we are experimenting with it. Visual navigation is another one, and onboard fault management. And especially, it would be, I'm pretty sure that it will be possible to detect, to forecast failures based on the data which is collected, and to forecast the failures on ground or directly on board. But again, we are now experimenting with it, not that it's working. There are some challenges to fly AI. Data quality. There is noise in space in the sense that there are all sorts of particles, you know, so you train on some data set on the ground, and then in space it could be different because there are some, you know, because of the radiation in the data, there are all sorts of bit flips and things like that. And then there are physical obstacles and particles, so the data looks different. So it can happen that the model actually does not work because you trained on different data set. So that's a tricky part. Robustness, but that's the usual problem with AI. Verifiability, maintainability, and I mentioned the computational power. I think I need to a little bit speed up. I wanted to mention this thing because it's about long-term maintenance. I already mentioned the spacecraft called Mars Orbiter, where it was important that you can update the software. But I just wanted to emphasize that sometimes, you know, first of all, you have to plan this. You have to plan that the software might be updated in the future. So you need to document, you know, to keep all the documentation, including the build process, you know, documenting the build process, keeping all the tools, like keeping GCC version from 20 years ago, just in case that you will need to recompile the software, you know. So it's not a trivial thing that you keep for a long time all your, I see that you are smiling because you had similar problem, right? It was presented yesterday. Yeah, and I wanted to just to point at this this gentleman who works for NASA JPL, David Cummings. He had a very nice talk at the Flight Software Workshop last year, which is called "How We Diagnosed and Fixed 2023 Voyager 1 Anomaly from 15 billion miles away. So basically what happened there, 47 years after launch, Voyager 1 stopped communicating or was communicating some noise. And then this gentleman with a team of guys were supposed to fix it. To send a command there takes over 22 hours. To get something back is over 22 hours, obviously, as well. It was documented on printed materials. He had to figure it out. He did not have any assembler, any simulator, any test bed. He did not have the source code. So in fact, he worked on the machine code, and he was able to really to debug on paper. I really recommend you to watch this presentation. At the end of the presentation, one of the questions from audience was, David, can you tell us who is your favorite actor to act yourself in future movie? Because it was really a really amazing piece of work. There's something similar with IOLU spacecraft. I will skip this, and I will skip mostly also this one, just for the sake of saving time. Another failure of our Proba mission earlier this year, and basically there was something like deadlock, wrong use of mutexes. And it's like you can find how to do it properly in every textbook, but still it happens. It's very complex code with many threads, many execution paths, many options. What is the sequence of using some shared resources and things like that? So it can still happen, and it did happen. So I guess lessons learned from this are maybe if you had better software architecture, some sort of framework, so that you are not using mutexes actually, you are using some higher level primitives, and maybe you are not fiddling with the mutexes, because otherwise you have to analyze it, and still it can happen that because of this, you might lose a spacecraft. And that's the next step towards a flight software framework. So between 2008 and now, we have been trying to have some sort of flight software framework, and we proposed one, we have one, which is based on some sort of execution platform and standard services on top of it. The execution platform contains operating system and some sort of middleware, and then you have some building blocks on top of it, some components which have provided and required interfaces and something like that. Why this is good? Because it makes us focus on mission-specific applications and not on something we fly every single time. We always fly the same infrastructure, roughly. So it enables reuse across missions, improves quality, reliability. Our problem is that we have not managed to use it beyond just reference architecture. So how we use it is that at least with our industry, because we have different suppliers and they've developed their own frameworks, so at least we use the same language so we understand each other, but that's it, basically. We don't have like a unified framework which everyone would be using in our business. We tried to standardize interfaces and we failed because that was not possible. And instead we started to think about at least standardizing how we specify interfaces, having some sort of formal specification of data interfaces. And that's something we call electronic data sheets. I wanted to talk about it because there was like an anomaly of Sentinel-2 where basically something called Star Tracker was misaligned because of wrong interpretation that the matrix should be transposed or normalized. And we took special care for the next release of Sentinel-2B. I was part of the team, so I know a lot about this. And despite all the effort, still, next time around, we made the same mistake that some matrix was actually wrongly understood not to be transposed. And again, there was some misalignment. So my point is, if we used some formal specification, and you can imagine that it's tricky to use formal description of a matrix and sort of give it a semantics to say how you should use it, whether it should be transposed or whether it should be normalized, because it sounds like plain English, it's difficult to find specification language to do this. But if we were able to do this, we would avoid these kind of problems. So basically, we really hope to do something like this, that from what we call electronic data sheet. We would be able to generate flight software, integration tests, simulation models, human readable description of interfaces. But we still keep working on this because it's difficult to make agreement across European industry. Future trends, as I said, large constellations and like industrial production of satellites. We will use more commercial off-the-shelf hardware, and then the software will be more complex because we will have to deal with failures because of radiation. Use of multi-cores, hypervisors, which will allow us to have systems which have different criticality on the same processor. And as I said, advanced autonomy, onboard data processing, AI-assisted end-to-end flight software development, more models, and two important things, and in some conversations I discussed it with some of you, and one of our strategic goals is actually to have European flight software framework, and I think that's your domain, so I would be happy to hear what you think about it. But really, it could be the European flight software framework could be a lot of things. You know, it could be, you know, ways of specifying interfaces, or it could be really infrastructure. You know, I can imagine different levels of alignment between all the suppliers in order to have interoperability between those suppliers. And software-defined spacecraft is another sort of buzzword. What it is about is basically to fly fewer number of processors and sort of by updating applications on those processors to change the function of the spacecraft. It's similar in cars. They would have tendency that you have the same box on lower class Mercedes and better class Mercedes, but by updating the software, you actually have better, I don't know what, one of the systems can be better version because it's better software, but otherwise the processor is the same. Finally, I was really, I'm sweat. I had to push all of the material through. So what I wanted to say, to repeat myself, flight software is critical. Spacecraft is as good as the flight software. It's common to underestimate the resources needed to do proper flight software. As I said, the way we see flight software is that we strongly focus on the development process. Things like software architecture, etc., maybe it comes from that you have good software architecture to be able to follow the process well. But that's not our focus. Our standards don't say how you should do your flight software architecture. Obviously, it helps a lot when you use modern tools. But anyway, proper software architecture and using software frameworks, we see it as a key thing, and makes reuse easier, and it helps you avoid common errors. Some of those I showed to you. The software code, which is behind all of these frameworks, is as complex as it always been. You know, when you get to the point that you need to, you know, fix a machine code because something is failing, you still have to understand all the details, how it's, you know, how the machine code really works. But if you can avoid it, at least during the development, it's good. But then there is, I guess, the tricky question, yeah, if you let AI do everything for you, who will be the expert to patch the code like David Cummings did with the Voyager 1? And then finally, yeah, I mean, some of it, what I presented, are lessons learned, showing freely mistakes we made. I strongly believe in this. Don't be ashamed of making mistake. Face it, share it, learn from it. Talk to people around because many of them know more than you do. And as the classic says, a mistake repeated more than once is not a mistake, but it's a choice. So by that, I finish. Thanks very much for your attention.